Hello everyone, this is Professor Keen. Today what I'd like to do is talk about Newton's laws of motion. I know I may have already talked a bit about this as an introduction to one of your lab experiments, but it's probably good to step back and just clearly go through Newton's laws of motion one more time. So this is from A Student's Guide to the Grade Physics Texts, Volume 2, Chapter 21, and the references, this is from Newton's Principia, Book 1. So let's jump right into Newton's laws of motion. So what I'm going to do is I'm going to put a title up here. Newton's laws of motion. And let's begin with Newton's first law. You might recall that Newton does not call these Newton's laws of motion. He calls them his axiom 1, axiom 2, and axiom 3. So in this lecture, what I think I'll do is try to get through axiom 1, and we'll see how we're doing. So let's start out by simply stating how Newton states his first law of motion. I'm going to write this out. He says that every body perseveres. So every body perseveres in its state of rest or of motion, or of uniform motion, in a right line. He uses the word right line. We would probably say a straight line, but that's okay. Unless it is compelled to change. Unless it is compelled to change that state by forces impressed thereon. So the idea is if you've got an object that's moving or is at rest, it tends to stay in that state unless there's an impressed force, that is some external force acting on it. Okay? So let me say a few things about this just to put this in perspective. So sometimes Newton's first law is referred to now as the principle of inertia. Okay, and you might recall from studying Galileo that Galileo invoked this, so it was used by Galileo when he was considering projectile motion. So in other words, Newton did not come up with the principle of inertia, or what we would call his first law of motion, rather just sort of got absorbed into what is now called Newton's laws of motion. Newton's laws of motion. Remember how Galileo used the principle of inertia? He said, well, if you've got like a cliff, let's say, and you've got a ball that's kicked off the cliff, it's going to follow a parabolic trajectory. And why does it follow a parabolic trajectory? It's because in the horizontal direction, it is experiencing uniform motion. And insofar as there is no drag exerted by the air, there is no horizontal impressed force. Therefore, whatever its motion was in the horizontal direction, it simply retains that state of uniform motion in the horizontal direction. However, in the vertical direction, as Galileo mentioned, it's undergoing uniform acceleration. In other words, initially it did not have any vertical motion, but as it falls off the cliff, it's acquiring more and more and more speed in the vertical direction. That is because there is an impressed force in the vertical direction. Newton would say that's because of the force of gravity. Galileo would say that's because of its weight. In any case, there's a uniform force downward, which gives it a uniform acceleration. Okay? So that's the principle of inertia. Maybe a few other just historical notes. This is very similar to, but not the same as, an older theory by a man named Jean Buridan, who lived in the 14th century, I think around 1301 to 1360 or so. Jean Buridan had something called, or he developed what is now called the impetus theory. And the principle of inertia is similar to this older impetus theory. And the idea of the impetus theory that was developed in the 14th century by the likes of Jean Buridan, and actually the idea goes back a little bit farther, but in any case, the idea is that when you apply a force to an object, that force delivers an impulse or an impetus to that object. And in so doing, it gives that object some momentum, we might say. It gives momentum to the object, and this momentum then carries the object forward until there's some kind of resistance, such as drag, that dissipates this impetus. So you get the same idea here as inertia. So an object that is given inertia retains that inertia as it moves forward. Jean Buridan, just as an aside, he was a student of William of Ockham. You might have heard of William of Ockham. Occam's razor is sometimes the philosophy that's associated with him, or the principle of parsimony. The idea, it's a philosophy of science that says if you have several possible explanations for some observed experiment, then one should take the simplest possible explanation that captures the behavior of that. So don't use complicated theories when a simple theory works. That's called the principle of parsimony, or Occam's razor sometimes. Incidentally, also, Jean Buridan was one of the fathers of what's called the commodity theory of money. He wasn't just interested in science. The commodity theory of money states that money, what do we mean when we talk about money? We don't necessarily mean dollar bills. What we mean, claimed Buridan, is that money is simply the most useful commodity that's around. So if seashells are the most useful commodity, then seashells will become money. If lambs are the most useful commodity around, then lambs will become money. And he also has a quote that says, this is again an economics idea, but he claimed that markets are amoral. That is, there's no morality in markets, they are amoral. But aggressive use of force is immoral. So if you aggress against someone else, that is an immoral or not moral action. But markets themselves are amoral. There's no morality, either positive or negative, in markets. So this is sort of the seen as a precursor of Austrian economics and the non-aggression principle of libertarian philosophy, which is kind of an interesting thing. Okay, let me say one other historical note here. So I've been talking about Galileo, Jean Buridan, and also let me mention Aristotle here by way of contrast. So Aristotle did not believe in inertia in the same way that Newton did. What he believed in his physics is that a body left to itself will seek its natural place. So a body left to itself will seek its natural place. So for example, if you have a clog of earth, like a clog of dirt right here, if it's left to itself, it naturally tends to go toward the center of the world, of the universe, according to Aristotle. So that's what it naturally does. So you leave a rock by itself, it doesn't continue in its state of motion or rest, as Newton and Galileo thought and Buridan thought, but rather it seeks to get to the center of the earth. And likewise, fire, if you light a fire, it tends to rise up. So those are natural tendencies of things according to Aristotle. So you see here Galileo and Newton were rejecting some of the ideas of Aristotle once again. Okay, so Newton's first law of motion. So let me just continue. Let me just state what Newton's second law of motion is, and then I will probably in the next lecture go into more detail about Newton's second law of motion. So what is Newton's, let me put quotation marks around this because this was Newton's first law of motion. Newton's second law of motion, and let me get rid of these because I probably won't need them. He says, the alteration of motion. The alteration of motion is ever, or always, proportional to the motive force impressed. And is made in the direction, I'll just state it first and I'll explain it. and is made in the direction of the right line, or the straight line. Newton says of the right line in which that force is impressed. Okay, so there you have it in text. Of course, he wrote it in Latin. This is an English translation, but let's see if we can figure out what he means by this. He says if you have some object, and you want to find how much its motion changes, and here you might think about the quantity of motion, or what we would now call the momentum. So there is a change in the quantity of motion, or the change in momentum. And how do you find out what the change in momentum of an object is? Well, it's proportional to the motive force impressed. So that is, if you apply some force to an object, its change in momentum is proportional to the force. Okay, so that's the first feature, that the change in momentum of an object, so I'll call this kind of subpoint one, the change in momentum is proportional to the impressed force. So if you have twice as big of a force applied, you get twice as big of a change of momentum. 3 times as big of a force, 3 times as big of a change in momentum. Okay, so that's the first thing. And the second feature of this law is not how big the change in momentum is, but the direction of the change of momentum. So he says the direction is in a right line or straight line in which the force is impressed. So in other words, if you apply a force in this way, then the change in momentum is going to be in the exact same direction as the force. If you apply a force this way, then the change in momentum is in the same direction. So there's 2 pieces of information in Newton's second law. First of all, the size of the change of momentum, and secondly, the direction of the change of momentum. Okay? So let me just remind you one other thing before we well, I want to talk a little bit more about Newton's second law, but let me just remind you of something I think I told you before. Let me just give some examples of this. Examples. Okay, so I'll do a few examples. Example A, let's suppose, for example, that we have a hockey puck that is sliding along the ice, and if this is really slippery ice, then when there's no force acting on it, then it's going to retain its state of motion. So this is law number 1. So when there's no force acting on it, it's just going to be sliding along with some momentum in that direction. Now let's suppose that you hit the back of it with a hockey stick. That is, you apply an impressed force, or a force, we would just say, to the back of the hockey puck. What happens is, because the force is in this direction, the change in momentum is in the same direction of the force. So if this was a situation before the force was applied, then after the force is applied, you're going to have a larger momentum. So this would be an initial momentum and the final momentum. So the change in momentum between here and here was just, I would say, maybe we could draw a little delta P, a change in momentum in the forward direction. So you're kind of adding this change in momentum to the original momentum to get this final momentum. Okay? Another example would be, let's suppose you have the exact same hockey puck that's sliding forward once again with some initial momentum in this direction. And now let's suppose we slap the front of this hockey puck with the hockey stick so that we apply a backwards force, a force in the backwards direction. Well, by Newton's second law, once again, the change in momentum is in the backwards direction. So after you hit it, now its final momentum is going to be slightly less than the initial momentum. Okay, so we take this initial momentum, we subtract off some momentum, or we add a momentum in the opposite direction, and we get the final momentum. Okay, so you might think of this column right here, a little bit messy, as being the before the force is applied, and this column right here would be after this force is applied. Okay, let me move this out of the way, put it over on the other side, and then let's do one more example and we'll stop for now. Let's suppose we have once again our hockey puck sliding with an initial momentum in this direction, And now we strike it on the top with the hockey stick. So we apply a downward force like this. Okay, well, what happens then? Well, we have a change in momentum in the downward direction, right? So now what's going to happen? Well, there's kind of a trick to doing this. I'm going to draw the initial momentum this way. That was the initial momentum. I'm going to take this little downward momentum. I'm going to add it in this direction, kind of putting the tail of this arrow, lining the tail of this arrow up with the tip of that arrow. And then the new momentum is just going to be like this. The final momentum, if you take the tail of the initial momentum and draw an arrow from the tail of the initial momentum to the tip of the change momentum, you'll get the final momentum. So what happens here is this change in momentum serves to change the direction of the momentum. And of course, these are three specific cases, but you can have combinations of these. So if you applied a force in some funny direction, you could speed up the object and change its direction, or slow it down and change its direction, for example. But these are three kind of typical examples of what you can do with a force to change the momentum of an object. And what I'm going to do is I'm going to stop there, and we can pick this up another time.